Welcome to another warm-up. Let's start this one by practicing some of those limits, not just the limit laws, but also some of the cases where we need to do a bit of extra work. So take 5-10 minutes, at least get far enough that you can recognize where you get stuck, and then we'll go through and do these together. Okay, little jump cut there while I gave myself some space. Hopefully you took a few minutes to work through those. Let's do them. So this first one is our best friend. This is an example of a polynomial, right? Just whole number powers on these x's and real numbers multiplying them out front, just adding and subtracting. And so what we learned last time is that we actually can just plug into this thing because it's a polynomial. Let's go ahead and plug in a little slower than I would normally. What we're really saying is that our limit laws let us look at each of these terms separately. And then as I look at this x to the 5, my limit law says I can just plug into x to the 5, which is a 32. And as I look at this x to the 4, I can just plug into x to the 4, which is a 16 times 2 is a 32 also. And then this negative 64 is just going to hang out and be itself. So this is just negative 64. So our limit law tells us that when we plug all this in, we get 32 plus 32 minus 64 is just 0. Easy peasy. So thanks limit laws for giving us this giant class of functions that we can take limits very, very quickly. I'm going to go through that concept a little bit slower just to practice those limit laws. What this is really saying, if I go all the way out, is that I can rewrite this as the limit of x, so as x goes to 2, to the 5. So I can split out this plus sign separately, and I can pull out that to the 5. Plus, I can pull out that 2, and I can do the limit as x goes to 2 of x all to the 4, and I guess minus, oh no, I just erased my whole thing, minus the limit as x goes to 2 of 64. This is a 2, this is a 2, this is a 64 because the 64 doesn't care what x does. And when I plug those in, I get this line right down here. In practice, we will not, for something like a polynomial, be breaking it up this much, but sometimes we will need to go in a couple of steps and actually use those limit laws to split things up a bit more. Often we will kind of play this slightly cheater game because we get a bit lazy and use arrows to say, hey, what we're really doing here is evaluating this quickly, because it can be a bit burdensome to do it longhand. Okay, next up, let's go on down. Here is the deal on this one. Notice that if I plug in a 0 into the top, I would get 9 minus 9. So the whole top is going to a 0, and the whole bottom is going to a 0. That tells us we have to do a lot more work. We really should try to clean this up. If the top was a 0 and the bottom was not, well, it would be 0, because like 0 over 5 is 0. If the top was not 0 and the bottom was 0, it's telling you that there's some kind of an asymptote going on, because as the denominator gets small, the whole thing gets really big. But when they're both 0, we don't know. We really can't say without cleaning it up a bit. So let's clean this up, and that's really going to be the game. If I try to expand this out a bit, I'm going to FOIL that out, and I should get a 9 plus 6h plus h squared. Being able to take squares quickly is going to be your friend in this class. Minus 9 all over h. And I often get the question, do I need to keep writing that limit thing? And the answer is yes. Yes, you do. Mainly because there's really a hidden equal sign out here, and I don't ever want you pretending that two things that aren't equal are equal, and they're not equal without that limit. It also leads to lots of other problems later on. So that limit is going to stick around. I'm going to go ahead and try to clean this up as much as possible. This 9 is going to go away with that 9. And I can cancel out some h's here. Let's do this in 2 steps so that my writing is clean. Maybe you could do it in 1 step on your own work. But the way I'm going to do this is pull out this h here. I get 6 plus h all over h. Why did I do that? Well, because now I can go ahead and cancel out those h's. Remember, you can only cancel h's from the entire top and the entire bottom. In other words, if you can factor it out so it's multiplying the whole thing, sometimes in the middle of a test, people are still tempted just to like cross out this h with that h and ignore one of the other terms, but it has to be the whole top and the whole bottom. All right, well, what is left now is keep my work clean, work in columns, always recommended. New column, limit as h goes to 0 of 6 plus h over 1. Now we can just evaluate. This, believe it or not, is a polynomial. If I plug in a 0 into this h, I just get a 6, and there is nothing wrong with that. Boom, I am done. Not so bad. So 0 over 0 means we got to do some more work to try to clean it up. Usually it means we need to try to factor out an h or whatever other letter is down here to get those zeros to cancel. That's what happened here. We kind of had a canceling in a controlled fashion. All right, one of the other ways that things can go awry is with piecewise functions. The question's off to the right, the limit as x goes to 0 of f of x, but f of x is this piecewise function. So the first thing you gotta do for a piecewise function is decide, okay, what piece of my domain am I in? Am I in the top? Am I in the bottom? In this case, I'm actually stuck in between the two. I'm on that breakpoint between the two. Even if it was a less than or equal, I would still be on that division between the two, because the limit doesn't actually care about what is at 0, just what is close to 0. Okay, so I can't just use the top or the bottom. That would be nicer. Instead, I have to use, do you know the answer? I gotta do two one-sided limits. So one of the reasons why this trips people up is because they forget about their friends, the old one-sided limits. Okay, why 0? Because that's this limit. From the left and from the right, because we have a theorem that says if the two one-sided limits agree, then we know the two-sided limit. So on the left, that means I am less than 0, which means that this function will just be sine of x. On the right, I'm bigger than 0, well then my f of x is just going to be x cubed. On that piece of the domain, close to 0 but bigger than it. And now I evaluate these two separately. Sine of x, a little tricky on my part. We haven't talked much about trig functions, but if I ignore them too long, people ignore them. So sine of x is a nice smooth curve. You could have used a table. I would forgive you for just looking at a graph right now, but really we get to just plug 0 into sine of x. Sine of 0, I hope you know. I hope it's quick in your mind. Sine of 0 is just 0. Okay, that's one of those you gotta just know. Like, yes, we love our calculators, but you need to know that sine of 0 is 0. And on that unit circle, it's just the height at the start of the unit circle, which would be on the x-axis. Okay, this one we actually have from a limit law. We can just plug into x cubed. It's also a polynomial, so this is 0. Our left and right hand limits, they agree. So if the left and the right agree, then the limit exists, and in fact it is the same as the left and the right. And so we get this beautiful answer here. Okay. If they did not agree, we would not have a limit, and we would have, in fact, a jump, unless one of them was infinite. If one of them was infinite, we'd have an asymptote. Cool. That's it for this warm-up. Hopefully that is a little bit of practice on taking limits under a few different circumstances. All right, enjoy the rest of the lecture.